Hey everybody. Today we're talking about the Poisson distribution. Suppose that we're interested in the number of times that some event occurs over a specified period, usually a period of time. For instance, the number of calls to a customer service line in a 10-minute period, the number of accidents along a busy stretch of highway in an hour, or the number of mistakes made by an amateur typist as they work through a 100-word paragraph. The number of occurrences of an event like this in a specified period can be viewed as a discrete random variable, let's call it x, whose support or list of possible values is the non-negative integers, 0, 1, 2, 3, and so on. If these events occur independently, they occur at a constant average rate and satisfy a few technical axioms that I'll get to at the end of this vid, then the random variable x is said to have a Poisson distribution. The probability mass function, or PMF, of random variable x with a Poisson distribution is given here. Lambda to the x times e to the negative lambda over x factorial, where lambda is a parameter for this distribution representing the average number of occurrences per interval of time. So what we're doing here is we are plugging in the number of occurrences that we're interested in, 0, 1, 2, 3, and so on, and getting back the probability of getting that many occurrences in the specified interval. For instance, if lambda is 2, then the distribution of x looks like this. When x is 0, the probability is, I would say, about 14%. When x is 1, the probability is going to be more like 27%, and so on. This probability histogram has a strong right skew, and its mode is just to the left of the mean x equals 2. And these are features that are common to Poisson distributions. Let's jump right in with an example. Around dinner time, calls to a pizza shop come in at an average rate of 1 every 5 minutes. What's the probability that there will be exactly 4 calls between 6:40 and 7 p.m.? What's the probability that there will be less than 4 and more than 4 calls in that period? First of all, we need to find the parameter lambda, the average number of calls in the interval of time in question. In this case, from 6:40 to 7 p.m., 20 minutes. Now we know they come in at an average rate of 1 every 5 minutes, so the average that we'll expect in a 20-minute period is going to be lambda equals 4. Now we can compute probabilities using that probability mass function. The probability that x is equal to 4 is going to be lambda to the x, so that's 4 to the x, in this case 4 to the 4th, times e to the negative lambda, e to the negative 4th, over x factorial, so over 4 factorial. Simplifying all that down, we get about 19.5%. The probability that x is less than 4 is going to be the sum of the probabilities for x equals 0, 1, 2, and 3. So, still keeping lambda equals 4, we plug in x equals 0, 1, 2, and 3. We get these decimal values that we can add up to get just over 43%. Finally, to get the probability that x is greater than 4, we're going to do this using a complement. We'll do 1 minus the probability that x is less than or equal to 4. So we're taking 1 minus 0.195, that's the probability that x is equal to 4, minus another 0.3433, the probability that x is less than 4. Overall, we get 37.2%. Another example. A bookstore keeps 5 copies of a popular cookbook in stock. Suppose the number of sales in a day follows a Poisson distribution with mean 4. What's the probability that the store can't meet its demand on a given day? In other words, what's the probability that the number of sales in a day is greater than 5? Again, we'll do this with a complement, 1 minus the probability that x is less than or equal to 5, that they sell no more than 5 cookbooks. Again, we're going to use that probability mass function, lambda to the x, e to the negative lambda over x factorial, this time plugging in the values between 0 and 5, and of course then subtracting the result from 1. After doing all that arithmetic, we get about 21.5%. Another question regarding the same example. How many copies should the store keep in stock so that the probability of turning a customer away is below 10%? We need to find a value, let's call it little x, such that the probability that our random variable comes out greater than that x is less than 10%. Or, to say it differently, such that the probability of our random variable being less than or equal to that value is at least 90%. This is an inverse Poisson calculation. We're given a probability and we need to get back a value, a certain number of occurrences with a corresponding probability. We can do this with technology, and in a video that I'll produce shortly, we'll see how to do this in R. Here, we're going to do it manually by constructing a cumulative probability distribution for this random variable x. We need to find the probability that x is equal to 0, that x is less than or equal to 1, 2, 3, 4, and so on, using that same formula, the same probability mass function that we've seen several times so far in this video. Doing a little bit of number crunching, we get these values: 1.8%, 9.2%, 23.8%, and so on. The probability of selling at most 6 copies is about 89%, so just under 90%, while the probability of selling at most 7 copies is about 95%. So if the store keeps 7 copies in stock, the probability of turning a customer away is well under that threshold value that we set of 10%. By the way, if we were using R to solve this problem, we would use the QPOIS command, QPOIS 0.9, 4. So I'm putting in the cumulative probability and the parameter lambda. Again, here we get the value of 7. Most theoretical derivations involving the Poisson distribution are based on the Maclaurin series for the exponential function. Here it is, just for review. E to the t is the sum from k equals 0 to infinity, t to the k over k factorial. Here I've written it kind of in calculus notation, where the summation is done over an index k. When we're doing things in stats, the summation is usually done over x, so just be aware of that distinction. For instance, suppose we want to compute the moment generating function, or MGF, of a random variable with a Poisson distribution. We would find the expected value of e to the t times x, and so we would plug in to get the sum from x equals 0 to infinity, e to the tx, lambda to the x, e to the negative lambda over x factorial. So I'm doing e to the tx times f of x, times that probability mass function. Since this is a summation over x, we can factor out the term that just has lambda in it, e to the negative lambda. And then notice that the thing in parentheses there can be treated as a variable. We can use that formula for the Maclaurin series at the top of this slide to simplify that entire summation down to e to the lambda e to the t. Rewriting this slightly, we get the traditional form for the MGF of a random variable with a Poisson distribution. E to the lambda times e to the t minus 1. Now, once we have the MGF, we can immediately get the expected value and variance of the Poisson distribution with parameter lambda. The expected value is going to be lambda, and the variance is going to be lambda squared. In other words, the standard deviation is going to be lambda. By the way, both the mean and variance can be derived directly without going through the MGF, but you're still going to be using that Maclaurin series for the exponential function. Let's do one more example. A machine producing cardboard boxes averages 2 flawed boxes per hour. First of all, let's find the expected value and standard deviation of the number of flawed boxes produced in an 8-hour shift. So basically we need to find lambda for the period of time corresponding to 8 hours. Well, we know the average number of flawed boxes per hour. We have 8 hours here, so we're going to do 2 times 8 to get 16. That's our lambda. So that's going to be our expected value and our standard deviation for this distribution. The variance, well, of course, would be 16 squared, lambda squared. 2. What's the probability that the machine produces between 12 and 20 flawed boxes in an 8-hour shift? So here I'm meaning to do between 13 and 19 inclusive, between 12 and 20 exclusive. So I want to sum up the probability mass function from x equals 13 to 19. When I do that, I get about 62%. The Poisson distribution is closely related to several other important distributions. 2 are particularly worth noting right now. First of all, the gamma distribution. This model's waiting time until a given total number of occurrences of an event are reached. with the same assumptions as with the Poisson distribution. These are easy to get confused when you're in an introductory stats class. The most important thing to keep in mind when you're trying to tell apart which one to use in a given situation is that the gamma distribution is going to be modeling a continuous random variable. Waiting times can be anything in an interval, while the Poisson distribution is modeling a discrete corresponds to a discrete random variable. 0 occurrences, 1 occurrence, 2 occurrences, and so on. Next, the binomial distribution, which models the number of occurrences of an event over a finite number of trials when the event has a fixed probability in each trial. By contrast, there are no individual trials for random variables with Poisson distributions. We could have events, in theory, occur as many times as you would like over any particular interval. So I promised that we would end by listing the technical requirements for a random variable to have a Poisson distribution with parameter lambda. So let's do that now as we wrap up. First of all, the Poisson distributions are going to assume that the number of occurrences in disjoint subintervals are independent. They don't affect one another. Secondly, the probability of exactly one occurrence in a sufficiently small subinterval of width delta t is approximately lambda times delta t, so proportional to the width of that interval. Finally, the probability of more than one occurrence in a sufficiently small interval, let's say again of width delta t, should be negligible. Now, in practice, these assumptions are never quite fully met, and so you'll frequently run into the phrase approximate Poisson process when describing situations in which they are reasonable simplifying assumptions.